Today we are going to discuss on a very important topic, which is about alkalis. All blast furnace operator knows that this is a very uh, impactful factor in blast furnace process optimization, and we all are aware about a higher percentage of alkalis presence could able to create many problems, including process instability, accretion, process upsets, losses of coke integrity, so higher fuel rate, so lesser productivity, irregular casting operations due to mug off of hearth, and so many things. Today we are talking about that what is that stringent band around which operators must have to focus, that this should be the K2O Na₂O band. As many authors has spoken so many things about the limitations, and I too come across other latest literatures and day-to-day analysis of the different furnaces data. uh, 3 kg per ton hot metal has been already mentioned in many of the documents. So operators need to come across these figure very seriously, and they have to meet it, because once we could not able to meet these, we could not able to keep our load below this figure, then it create a problem in the furnaces, as I have already refined, and all operators knows about the detrimental effect of K2O NO2, out of which K2O have a more significant effect than Na₂O. So if we have to choose that out of K2O and Na₂O, which is more detrimental, we can straight say that K2O is more dangerous. And number two is, what should be the limitation? The limitation is 3 kg per ton hot metal. Load is to be monitored around that. Now coming to the second slide is just a revision of the alkali behaviors in the furnaces, as a slide has already shown, where from the 1500 degrees centigrade, which is the twin zone area, how the alkali oxides are getting reduced by the equation it has already notified. Thereafter, once we know that reduction is over, then potassium and sodium has a very important property of this vaporization temperature, which is very less. And as it is well marked on the slide for better understanding to the operator, that potassium boils at 760 only, whereas sodium boils at 883 degrees centigrade. So at this temperature immediately they volatile, and as we come across, the reduction is already happening at wear zone. So immediately after reduction, once it comes under a sodium potassium form, it volatiles, and this then the third part is the reoxidation in the upper area. What happens that this sodium and potassium gets find a location of 700 1000 zone, where the cooler zones are there, which where this sodium and potassium component gets hidden, or we can say condensed there, and at the same time the upcoming CO2 and oxygen and the gases is come in contact with these potassium and sodium to form K2O and sodium carbonate, as it is already in the third row equation has already signified. Now coming to the detrimental effect and its value in terms of the losses, in terms of the problems happening in the furnaces, is like this, that once we touch upon the level of 3 kg per ton hot metal, then our coke consumption gone up by 18 to 33 kg per ton hot metal, which is a big value. And as you must be knowing that for each unit of alkali content, our fuel rate deviated in band of 6 to 11 kg, which is a huge value. At the same time, this increase in coke consumption due to higher alkali content, that is almost 3 kg per ton hot metal band, our production decreases by 13.5% as coke rate is increasing. Now coming to the part where we want to sensitize the operator that when the band is go beyond 3, and once it go beyond 3, then we are losing almost more than 33 kg per ton hot metal, and in the process we can say that production loss is go beyond 13.5%. And apart from this is not the enough, apart from these we have a hanging, sleeping, refractory losses, scaffold formation, accretion, bad utilization, and asymmetric operation of the furnaces keep the operators on risk situation, and it badly affect the total shop performance. Now coming to the different furnaces data compared to for comparing K2O inputs, and as we come across the worldwide value is around 1.2 to 1.7 and 1.8. uh, so and one more thing is that we have to find out that K2O is very harmful compared to Na₂O. As one very important thing in support of this statement, I want to give that if we come to a lower temperature, then we can see that retention of K2O in the slag is very good. But as temperature goes up, the K2O retention is getting reduced, and thus K2O keep on circulating in the furnaces. So K2O recovery is more challenging than Na₂O, where Na₂O remains almost stable within this lower temperature range or higher temperature range. So you can say that K2O is more challenging in handling, and thus each one operator of the blast furnace should more focus on K2O rather than Na₂O. Of course, K2O Na₂O total value is also important in terms of accumulation of alkali load in the furnace and its detrimental effect in due course of time. As this is the mitigation plan once we come across this type of situations, and we can say that in view of alkali load monitoring and subsequently coming with the result that it is difficult to manage, then these are the way outs which can helps operators, especially blending a different type of force which can nullify the alkali loads. The basicity is a very important tool which can helps the operator to flush the K2O and Na₂O, and for this we need to come across a lower basicity. Of course, the consequent of this lower basicity is getting reflected in hot metal sulfur, and in order to meet this we need a external desulfurization. So we can say these overall three components could able to take care of the alkali managements. Apart from these, operator can aim a better optic temperatures in their furnaces. I mean to say that the temperatures must be beyond 100 degrees centigrade as a fundamental, and of course some many times many operators to say that lowering the stock lines for a temporary time also is a good measure to handle the alkali loads, out of which these three are prominent. Thank you.